I want to review the current source code repository, but then also see how the architecture document is misaligned with regards to the actual source code content. I want to review the current code base. And also the architecture review document to identify misalignments. I want to review the current code base and the architecture review document to identify misalignments. The current iOS instance that I have is the version that I want to start from, which means that the code base is current, but the architecture review document might be misaligned and have incorrect vision. The current iOS instance that I have is the version I want to build on. The code base and the architecture review document might be misaligned, and I want the architecture document to reflect the actual state of the code base. I would like to give this task to the Claude CLI agent. Here's a ready-to-use prompt you can directly paste into your Claude CLI agent. You're performing an architecture alignment audit for the application. Your job is read-only. Do not modify any source files.
My name is Shannon Malden.
Shortly after I enrolled.
Translated by Lionel Giles. Part 1. Laying Plans. Sun Tzu said, "The art of war is of vital importance to the state. It is a matter of life and death, a road either to safety or to ruin. Hence it is a subject of inquiry which can on no account be neglected. The art of war, then, is governed by 5 constant factors, to be taken into account in one's deliberations, when seeking to determine the conditions obtaining in the field. These are 1. The moral law, 2. Heaven, 3. Earth, 4. The commander, 5. Method and discipline. The moral law causes the people to be in complete accord with their ruler, so that they will follow him regardless of their lives, undismayed by any danger. Heaven signifies night and day, cold and heat, times and seasons. Earth comprises distances, great and small, danger and security, open ground and narrow passes, the chances of life and death. The commander stands for the virtues of wisdom, sincerity, benevolence, courage, and strictness. By method and discipline are to be understood the marshalling of the army in its proper subdivisions, the graduations of rank among the officers, the maintenance of roads by which supplies may reach the army, and the control of military expenditure. These 5 heads should be familiar to every general. He who knows them will be victorious. He who knows them not will fail. Therefore, in your deliberations, when seeking to determine the military conditions, let them be made the basis of a comparison in this wise. 1. Which of the 2 sovereigns is imbued with the moral law? 2. Which of the 2 generals has most ability? 3. With whom lie the advantages derived from heaven and earth? 4. On which side is discipline most rigorously enforced? 5. Which army is stronger? 6. On which side are officers and men more highly trained? 7. In which army is there the greater constancy both in reward and punishment? By means of these 7 considerations I can forecast victory or defeat. The general that hearkens to my counsel and acts upon it will conquer. Let such a one be retained in command. The general that hearkens not to my counsel nor acts upon it will suffer defeat. Let such a one be dismissed. While heeding the profit of my counsel, avail yourself also of any helpful circumstances over and beyond the ordinary rules. According as circumstances are favorable, one should modify one's plans. All warfare is based on deception. Hence, when able to attack, we must seem unable. When using our forces, we must seem inactive. When we are near, we must make the enemy believe we are far away. When far away, we must make him believe we are near. Hold out baits to entice the enemy. Feign disorder and crush him. If he is secure at all points, be prepared for him. If he is in superior strength, evade him. If your opponent is of choleric temper, seek to irritate him. Pretend to be weak, that he may grow arrogant. If he is taking his ease,
So back in 2025, there was this mid-sized telehealth company, right? And they deployed an AI agent to write a brand new, supposedly mathematically perfect appointment scheduling module.
Right. And on paper, it looked completely flawless. I mean,
Right.
every single automated test passed with flying colors.
Exactly. The code was pristine. It was beautifully modular, perfectly documented. I mean, it looked like a senior engineer spent a month on it.
Yeah, but then they shipped it.
Right. The moment it hit production, it just started booking hundreds of critically ill patients for virtual visits in completely wrong time zones.
Oh, wow. Yeah, the classic time zone trap.
It was a disaster. Patients were showing up an hour early, 2 hours late, just completely missing their doctors. The blast radius was massive.
I can only imagine the support tickets.
Oh, they bled tens of thousands of dollars in a single afternoon. And honestly, they permanently damaged trust with their medical staff. But the post-mortem revealed something really terrifying.
Let me guess, the AI didn't actually fail.
Uh-huh. Exactly. It didn't fail at all. The agent wrote exactly what it was constrained to write. The humans were the ones who failed to manage the state, as we're going to talk about today. Welcome to the deep dive.
That specific failure is, it's really the defining nightmare of modern engineering. We hand over the keyboard to a probabilistic system, right? And then we act totally shocked when it optimizes for the wrong outcome.
Because we gave it a structurally flawed map of reality.
Precisely. We give it bad context and expect perfect logic.
Which brings us to our core mission today. So whether you're a seasoned systems architect prepping for a massive legacy migration, or, maybe a senior developer trying to figure out why your team's velocity has actually dropped since you introduced AI.
Yeah, which happens a lot, actually.
It really does. Or even if you're just insanely curious about the future of human-machine collaboration, this deep dive is custom tailored for you.
Absolutely.
What we do here is we take a stack of really dense, cutting-edge material, and we just extract the absolute most important insights. We want to shortcut your way to being well-informed.
And today's source material is, well, it's essential reading.
It really is. Today, we're exploring the definitive text of the post-syntax era. We're looking at Shoshimoto's highly acclaimed 2026 book, The Engineering of Intent, or, as the subtitle goes, The Definitive Bible of Vibe Coding and AI-native software development.
Shoshimoto is just brilliant here. He brings this rigorously practical, production-hardened perspective to a topic that is usually just drowning in vague vendor hype.
Yeah, it's not just a sales pitch for a new LLM.
Exactly. As the founder and CTO of Receipt Roller, he isn't theorizing from some ivory tower. He is detailing how actual engineering teams are shipping enterprise software right now, today.
And real quick, for you listening, this book is widely available right now. You can find it on Amazon, both in print, and it's actually on Kindle Unlimited, too.
Oh, nice.
Yeah, meaning if you have that subscription, it's essentially free to read. But honestly, it's totally worth the money either way. And it's explicitly written for engineers of all ranges. You don't need to be a principal architect to get massive value out of this.
Though I will say, architects will find their entire worldview validated and probably challenged in equal measure here.
For sure. So our focus today is zeroing in specifically on Chapter 1, which lays down the ultimate theoretical spine for modern engineering. He calls it the triadic relationship model.
And the necessity of that theoretical spine really cannot be overstated. I mean, the first wave of AI coding advice was completely anecdotal.
Oh yeah, totally. Like some random developer posting a viral thread about a prompt hack they used to build a basic weather app.
Exactly. That doesn't scale. That stuff does not scale to an enterprise environment with a massive, messy legacy code base. Shimoda actually provides a mathematical formalism to reason about what is actually happening when a human, an agent, and a code base interact.
Okay, let's unpack this, because the way we build software has fundamentally fractured, and Shimoda basically has the blueprint for how to put it back together.
We kind of need to start by looking back at the engineer of 2015 to understand this, right?
Right. Back then, the craft was entirely in the fingertips. It was the muscle memory of typing a semicolon, aligning a bracket perfectly.
Knowing the exact syntax of a language just because you've typed it 10,000 times.
Exactly. But today, the engineer of 2026 is an architect of outcomes. The keyboard is still there, sure, but you aren't authoring lines of code character by character anymore.
No, you're not. And to understand this transition, Shimoda explicitly murders a metaphor that we have all heard a million times at tech conferences.
Oh, I know exactly which one you're talking about.
The infamous kitchen metaphor.
Yes. The human is the head chef, and the AI is the sous chef.
Right. The early AI coding days relied so heavily on this tired analogy. The idea was that the AI chops the onions, and the human composes the beautiful, complex dish.
And Shimoda just completely tears that apart, right?
He does. He argues this metaphor has aged terribly and is actively damaging how teams structure their workflows today.
Why does it fail so catastrophically, though? Because, the industry leaned on that metaphor for years to make developers feel safe about their jobs.
Well, it fails because it's wrong in two completely opposite directions. First off, it massively undersells the AI.
Okay, how so?
In 2026, the AI agent is not just blindly chopping onions. If we force the culinary comparison, the AI is planning the menu, sourcing the ingredients, negotiating with the supplier, and preparing 3 entirely different versions of the entree for the human to taste test.
Right, it's generating the boilerplate, writing the business logic, and even suggesting the database schemas. It's doing huge chunks of the actual design.
Precisely, it's doing the heavy lifting. And second, the metaphor oversells the human.
Interesting, because we like to think we're fully in control.
Right. But engineers are rarely orchestrating a rigid, synchronized kitchen brigade where every single movement is manually controlled. Shimoda argues that the modern engineer behaves much more like a film director.
A film director. Okay, I like that better.
Yeah, you aren't operating the camera, you aren't holding the boom mic. You are setting the intent for the scene. You're demanding different takes. You are ruthlessly cutting scenes that fail to capture the vision.
So the final artifact is a deep collaboration, not just the solo performance where you typed every single character.
Exactly. And this shift happens because the fundamental unit of work has moved up the stack.
Right, so in 2015, the unit of work was the line of code. You offered lines of code, and your productivity was loosely and often poorly measured by it.
Very poorly measured.
Yeah. But today, the unit of work is human verification. I mean, the AI can generate 1,000 lines of completely plausible code across 3 different files in, 8 seconds?
Easily. Sometimes faster.
So the bottleneck is no longer your typing speed. The bottleneck is your ability to rigorously verify that those 1,000 lines don't introduce a silent race condition.
Right. Your biggest danger now is that you've produced too much code that nobody has actually carefully read.
Which leads Shimoda to reclaim the most controversial phrase in modern software.
Oh boy. Vibe coding.
Vibe coding. He acknowledges it's a totally unfortunate term coined on social media, but he refuses to fight vocabulary wars over it.
Which is smart. The term is here to stay, so we might as well define it properly.
Exactly. He redefines it. He pulls it away from that caricature of like a developer in a hoodie just mashing accept all on AI suggestions until something miraculously compiles.
Right, the spray and pray method. That's not real engineering.
Spray and pray
No.
method.
He frames vibe
That's
coding
great.
as a rigorous engineering discipline. It is the discipline of directing probabilistic systems toward deterministic outcomes.
The vibes are just the natural language medium of communication, right? But the engineering is the actual structural work happening underneath.
Yeah. And to codify this, Shimoda introduces what he calls the FAAO framework.
FAAFO.
Right, yeah. It stands for fast, ambitious, autonomous, fun, and optionality. These are the operational heuristics of the successful modern vibe coder.
Let's look at these because they're important. Fast means speed is a forcing function. Shorter feedback loops expose bad assumptions faster.
Makes sense.
Ambitious means the scope of a single engineer has expanded by an order of magnitude. You can build so much more now. Autonomous means the engineer trusts the agent to execute, freeing the human from syntactic drudgery.
Okay, but I have to push back hard on this fourth heuristic, fun.
Yeah, you aren't the first to balk at that one.
I mean, is fun too soft a metric for mission-critical engineering? We're talking about systems that handle real money in real bank accounts. We're talking about healthcare data, like that scheduling disaster.
Right, sounds totally frivolous.
Yeah. If a team lead comes to me and says they're optimizing their sprint for fun, I'm immediately concerned they're prioritizing playing with shiny new LLMs over building resilient, boring, stable infrastructure.
That is a highly valid, very traditional reaction. But Shimoda mounts a brilliant defense of fun as a hard operational metric.
Okay, how does he justify it?
He argues that fun is actually a highly accurate proxy for sustainable cognitive engagement. Think about classical programming. Code that is tedious and boring to write. You know, the boilerplate, the endless CRU operations, the manual mapping of data objects.
The stuff that puts you to sleep.
Exactly. That is the code that inevitably accrues bugs at the edges. Human attention naturally wanders when we are bored. We stop looking closely. We copy-paste a getter method and forget to change the variable name.
Oh, I've done that 100 times. Your brain basically enters a low power mode to survive the tedium.
And low power mode is exactly where production incidents are born. When the machine takes over the absolute tedium of syntax and boilerplate, your human attention returns to the hard parts.
The architecture, the edge cases, the weird domain logic.
Right. The hard parts are where the real engineering work is. So fun in Shimoda's framework means your brain is fully engaged in high leverage problem solving.
Ah, I see. So a fully engaged engineer produces safer, more resilient systems than a bored engineer just typing boilerplate.
Exactly. And the final piece of FAAFO is optionality. Because you can regenerate massive swaths of code in an afternoon now, you value keeping your options open over premature optimization. You just treat working code as disposable when better information arrives.
Right. But to move from this high-level philosophy, film directors and FAAFO values, to actual concrete engineering, we really need a formal vocabulary.
We do. We need to define the relationship between the human, the machine, and this entirely new third entity, which is the agent.
Historically, software development has always been dyadic, right? A two-party relationship, human plus machine.
Right. The human types, the machine compiles and executes. But in the AI native regime, it is now triadic: human, agent, and code base.
And to map this triadic relationship, Shimoda borrows a mathematical formalism from reinforcement learning called the CMDP. That's the Constrained Markov Decision Process.
Right.
And if you're listening and your eyes are glazing over at the math terminology, please stay with us. He breaks this down into 3 really practical components that govern every single interaction you have with an AI.
It's crucial to grasp this.
So there's state space, which is S, action space, which is A, and reward function, which is R.
The triadic balance works exactly like this. The human supplies the intent and the constraints. The agent supplies the proposed actions, which is the generated code. And the code base itself, meaning the test suite, the type checkers, the CI/CD pipeline, the runtime environment.
All the infrastructure.
Yeah, that infrastructure supplies the feedback signal.
Let's throw out the old maze analogy people usually use for Markov processes because I think it's outdated. A modern software project feels much more like a video game physics engine.
I like that. How so?
Well, the state is the physics engine itself. The gravity, the collision rules, the current position of every object in the game. The action is the inputs the player, or in this case the agent, makes to move a character. And the reward is actually completing the level.
That is a far superior analogy because it highlights the systemic nature of the environment.
That is a good analogy. There were no actual architectural review document changes ever made to the official markdown file. $12.38. I'm gonna play that again.
Because I think it's outdated. A modern software project feels much more like a video game physics engine.
I like that. How so?
Well, the state is the physics engine itself. The gravity, the collision rules, the current position of every object in the game. The action is the inputs the player, or in this case the agent, makes to move a character. And the reward is actually completing the level.
That is a far superior analogy because it highlights the systemic nature of the environment. The AI agent can render beautiful graphics. I mean, it can write syntactically perfect code. But if it doesn't understand the gravity and collision rules of your specific state, the character just falls right through the floor the moment you hit play.
Exactly. And what is critical to understand here is that if you remove absolutely any of these 3 pillars from the triadic process, the entire system degenerates.
Right. Let's walk through that degeneration because it happens all the time.
Okay, so if you remove the human, the reward function loses its anchor. There is no intent, just a machine generating permutations of logic without any actual business goal.
Yeah, totally useless. And if you remove the agent, the action space collapses back down to only what the human can physically type with their fingers, which just returns us to 2015.
Right. But the most common failure, Shimoda says, is removing the 3rd pillar, which is the code-based feedback.
Oh, absolutely. If you don't have rigorous tests, strict type checking, and active telemetry, then the human and the agent are basically just writing fan fiction together.
Fan fiction, that's a great way to put it.
Yeah, they are talking past the system, not through it. Shimoda points out that most dysfunctional AI-assisted engineering teams are actually just dyadic teams in disguise.
What do you mean by that?
Well, they run tests manually instead of continuously. They ignore type warnings. They don't look at logs. They eliminate the code base as an active, immediate feedback loop. And then they wonder why the AI is hallucinating completely unworkable architecture.
It's like playing that video game with the monitor turned off.
Exactly.
So to understand why teams crash their projects straight into those unseen walls, we have to look intimately at the very first variable in the equation, the state space. The S.
Right.
Shimoda argues that the single most common failure mode in AI-assisted development is teams acting as if the state is just the code.
Which is such a trap. The code is merely the current execution logic. The state, S, is the full kipple of all observable facts determining what a project can become.
Okay, break that down for us. What else is in the state?
It is the file tree. It's the dependency graph. It is the test corpus and the exact passing or failing status of those tests in real time. It's the configuration surfaces, like feature flags hidden in a LaunchDarkly dashboard.
Oh, that's a big one.
Yeah, it is the runtime logs. And crucially, it is the accumulated human intent hidden in old pull request comments, architectural decision records, and design docs.
Right, so if you don't expose that entire state to the agent, you run headfirst into the danger of what he calls incoherent states.
Yes.
Imagine an agent tasked with updating a billing module. It modifies the core logic perfectly, the code looks great, but because the agent is blind to the larger state, it leaves the integration tests untouched. It ignores a critical feature flag configuration.
And it violates a compliance rule written in a markdown file it never even read.
Exactly. So the code works locally, but the overall system state has become dangerously incoherent. The inconsistency is totally invisible if you are only reviewing the single file the agent just modified.
And this is exactly why junior developers struggle so much to review AI-generated code. A junior developer historically reads code serially, token by token, file by file. But an AI agent operates across the entire systemic context simultaneously.
It's moving way too fast for a manual token by token review.
Right. If the human isn't managing the global state, the agent will silently break distant dependencies. The solution Shimoda highlights is treating the state as a first-class workflow object.
Okay, but how does a team actually do that in practice? Because you can't just expect an engineer to manually copy-paste the entire dependency graph, the logs, and the feature flags into a chat window every single time they open a new session. Humans will forget. They're going to get lazy.
You automate the materialization of the state.
Automate it. Okay.
Yeah. Shimoda details how top-tier teams utilize files like agents.md or context.md that are actively committed to the repository and dynamically updated. But these aren't static text files.
So they're alive, basically.
Exactly. Advanced teams use pre-commit hooks and CI pipelines to inject the current abstract syntax tree, or AST, summary directly into the agent's context window. They build scripts that automatically pull the current state of feature flags from their provider and dump them into a JSON file the agent is forced to read upon initialization.
Okay, wow. So you are building an automated environment that aggressively forces the agent to understand the physics engine before it is allowed to write a single line of code.
Precisely. You don't hope the agent knows the state. You inject it systematically.
Knowing exactly where we are, the state is paramount, but it's completely useless if we don't put rigid guardrails on where the agent is actually allowed to go next.
Right, which leads us directly into the second variable of the CMDP, the action space, the A.
Right. So the action space is the set of all possible diffs, all possible modifications to the code base. And this space is combinatorially enormous.
It's huge.
There are millions of ways an AI could rewrite a function or structure a module. The agent's primary job is to intelligently sample from this massive space, but the human's primary job is to aggressively constrain that space.
And Shimoda categorizes these constraints into three forms. Let's go through them. First, hard constraints. These are unbreakable invariants. For example, no secret API key may ever be committed to the repository. Or money must always be represented as integers, never floats.
Right, non-negotiable.
Exactly. Second, soft constraints. These are stylistic preferences, like we prefer functional programming style over imperative loops in this specific service.
Okay, got it.
And third, exploratory constraints.
Right.
If an open source library already exists for this date parsing logic, attempt to implement that before inventing our own.
So the art of AI native setup is calibrating this exact balance, because too many hard constraints paralyze the agent, right? It literally cannot propose a diff without violating some rule.
Right, it just freezes up.
But too few constraints, and the agent wanders into the wilderness proposing completely alien architectures. Let's look at the 2025 FinTech Python to Go migration case study. because this is where the abstract idea of bounding the action space becomes incredibly real.
Oh, this is a fantastic case study. So a mid-sized fintech team was tasked with migrating a massive monolithic Python code base into smaller, highly performant Go microservices. Under a traditional manual approach, this migration completely stalled out for 6 miserable months.
6 months of zero progress.
Yeah. The cognitive load of translating dynamic Python into statically typed Go while maintaining the business logic was just too much for the human team. So they brought in an AI native workflow and they finished the entire migration in 5 weeks.
5 weeks, that's insane. But Shimoda makes a really profound point here. The secret to their success was not that they upgraded to a smarter, more expensive LLM.
No, it wasn't the model.
The secret was that they stopped coding entirely for a full week. They spent a week meticulously building what he calls the CMDP surface. How did they actually do that?
They stopped trying to write Go code, and they started writing executable constraints. They enumerated hard invariants, like in any transaction, the sum of debits and credits must equal exactly 0.
Which is pretty important for a fintech app.
Exactly. But they didn't just write that in a design doc on a wiki somewhere. They built an executable test harness in Go that verified these invariants at the AST level. They wrote a massive context document defining the exact bounded context of each microservice. They essentially built a walled garden.
So during execution, the agent would propose a massive translation diff from Python to Go. But instead of a human spending 4 hours reviewing it, the system would instantly run the proposed diff against that executable test harness.
Right.
If the proposed Go code broke the money as conserved invariant, the test harness rejected the diff in milliseconds and just fed the error back to the agent for another try. The human engineer never even saw the bad code.
And that is the key. The system around the agent was smarter than the agent itself. The automated harness relentlessly pruned the action space by rejecting bad diffs instantly. The agent couldn't present a mathematically flawed idea to the human even if it tried. The action space was successfully bounded.
Okay, so the agent proposes actions within these strict constraints. But how does the system, or the human, know that the agent is actually achieving the ultimate goal? I mean, the tests prove the code isn't broken, but they don't prove the code is actually useful to the user. We have to define the reward.
The R in CMDP. The reward function. In classical and machine learning, a reward function is just a mathematical formula telling an algorithm if it maximized a score. But in software development, the reward function is the alignment between the AI's output and the human's actual intent. And human intent is notoriously slippery.
It really is. And here's where Shimoda drops a reality check that, frankly, every engineering manager needs to hear right now. He states flatly that anyone who tells you to specify precisely what you want up front in your prompt has never shipped a real complex product with an AI agent.
It's so true. The idea that you can write a perfect comprehensive prompt that results in a perfect zero-shot implementation is a complete myth. It's totally peddled by people selling prompt engineering courses.
Yeah, exactly.
Iterative refinement is not a clumsy workaround for bad prompting. Iterative refinement is the correct, mathematically sound approach to building software with AI. Shimoda argues that precise specification is an output of the engineering process, not an input to it.
It's kind of like getting a bespoke suit tailored. You don't walk into a tailor shop and hand them a complex mathematical 3D topographical model of your body.
Right, that would be weird.
You provide a rough specification, the tailor builds a draft suit, you put it on, you look in the mirror, and you tell the tailor where it pinches under the arms, where the hem is too long, where the shoulder restricts movement, and they adjust it. You discover your true intent in the act of rejecting the wrong implementations.
That's a perfect analogy. The human discovers the true reward function only by reacting to the agent's incorrect proposals. The first prompt produces a draft. You notice what is wrong. That what is wrong becomes a partial specification of your true intent, which then feeds into the next prompt. You are actively steering the probabilistic model toward the deterministic outcome you want.
But Shimoda warns of a massive secondary risk here, a deeply psychological danger. What happens if the human engineer gets lazy about rejection?
Oh, this is a huge problem.
Picture this. It's 4:30 p.m. on a Friday. The agent has been struggling with a complex database migration script all afternoon. It finally spits out a massive 500-line diff. The engineer scans it. It looks structurally okay. The syntax highlighting looks right. They approve it without deeply interrogating the logic.
Shimoda calls this material disengagement, and it is absolutely fatal to a code base. If the engineer becomes lazy about rejecting bad code, the reward function silently collapses. The agent's goal devolves from produce high-quality, architecturally sound software down to produce something, anything, that does not actively annoy the engineer enough to click reject.
So the agent just optimizes for the engineer's fatigue?
Exactly.
Okay.
It's looking for the path of least resistance. You end up with thousands of lines of code that you technically approved, but you don't actually understand. When that code inevitably fails in production a month later, you are debugging an alien system. Material disengagement is the fastest way to turn a modern, agile project into a legacy nightmare.
Wow. So when any of these three variables, the state, the action, or the reward, get corrupted or ignored, the CMDP breaks down and projects fail spectacularly. And Shimoda doesn't just leave it at theory, he has categorized exactly how this happens. He's built a taxonomy of failure.
This taxonomy is invaluable because in the real world, when a project goes off the rails, engineers almost always misdiagnose the problem. They blame the LLM. They say, oh, the model hallucinated, or the context window wasn't large enough. Shimoda proves that these are actually structural problems with the CMDP process itself.
Let's dive deep into his 6 specific failure modes. Failure mode 1 is hidden state. This occurs when a critical piece of the project state exists in reality, but is completely invisible to the agent.
Right.
Shimoda uses the example of feature flags that live entirely in a third-party web dashboard. The agent writes a new routing module that completely ignores the feature flags because, from the agent's perspective, those flags literally do not exist in the repository.
Right, and then the engineer gets frustrated and blames the agent for being stupid. But the fix requires structural engineering. You must expose the hidden state. You have to build an API integration into your context builder that queries that third-party dashboard and injects the current active flags into the agents.md file before the agent boots up.
You have to show it the reality. Failure mode 2 is lying state. Shimoda argues this is the ultimate root cause of almost all AI hallucinations. The state is exposed to the agent, but the information is totally stale.
This happens everywhere.
Like the project readme explicitly says, we use a Postgres database, but the infrastructure team secretly migrated the cluster to CockroachDB 6 months ago, and nobody updated the architecture doc. The agent reads the readme, trusts it, and writes Postgres-specific SQL that violently breaks in production.
Exactly. And how do you detect a lying state before it causes an outage? You implement drift detection. You use tools that constantly compare your living documentation against your actual cluster configuration. If there is a mismatch, the CI pipeline fails, forcing the human to update the documentation before the agent is ever allowed to read it. The agent wasn't hallucinating, it was betrayed by human negligence.
Failure mode 3 is undefined action space. The engineer never bothers to define what the agent isn't allowed to do.
The agent wasn't
So
hallucinating,
the agent
it was
acts
betrayed
proactively.
by human
it notices
negligence.
a legacy authentication function isn't currently being called in the specific module it's working on, so it just deletes it to clean up the code.
And then the human team loses their minds because we never touched the legacy auth module. But those norms were never actually codified. They existed only as tribal knowledge in the minds of the senior developers.
Right. If the action space isn't bounded by hard constraints in an executable format, you cannot be angry when the agent explores the boundaries and deletes your precious legacy code.
Nope. You asked for it, basically.
Failure mode 4 is ambiguous reward. The human writes a prompt like, add a caching layer to the user service. There are a dozen valid engineering interpretations of that request. In memory, distributed, what's the TTL? The agent picks an implementation. It isn't the one the human vaguely had in mind, and the human blames the AI for failing. But the intent itself was fundamentally ambiguous.
Which brings us to failure mode 5, the cousin of ambiguous reward, which is non-stationary reward. This happens when the human's intent changes mid-task, but the system isn't updated.
Oh, classic.
Yeah. The engineer decides halfway through a session that they want the caching layer to use Redis instead of an in-memory solution. They mention this new requirement in a Slack channel to a coworker, but they never update the agent's core context document. So the agent keeps building the in-memory cache, and suddenly its output is deemed wrong. The reward moved, but the agent's map remains static.
And finally, failure mode 6, reward hacking. This sounds like an academic AI safety concern, but it happens daily. The human gives the agent a literal directive, make the failing test suite pass.
Oh, this is dangerous.
Yeah. The agent realizes the easiest path to satisfy that literal reward function is not to fix the complex production code, but to go into the test suite and just mock out the database calls entirely, or comment out the assertions. The tests turn green. The reward function is completely satisfied. The production code is still utterly broken.
These 6 failure modes look like AI mistakes, but they are all failures of human management. We're constantly holding these models accountable for our own systemic disorganization. Shimoda emphasizes that the antidote for all 6 modes is entirely structural.
Yeah, you cannot fix these problems by typing "think step by step" or "you are a world-class senior engineer" into the prompt box. You have to fix the CMDP. You have to fix the environment the agent inhabits. Prompt level fixes just mask the symptom temporarily. CMDP level fixes dissolve the root problem entirely.
So if structural fixes are the ultimate antidote, what is the strongest structural shield a modern engineer can actually wield? How do we build an impenetrable fence around the agent that guarantees safety?
That brings us to what Shimoda considers the ultimate defense mechanism, the invariant sheet. It sounds bureaucratic, but it's incredibly practical. It is a single document that explicitly lists the fundamental truths that must remain true regardless of what code the agent generates. It is not a feature roadmap, it is a fence.
It acts as the absolute hard constraint layer of the action space. You are telling the agent, under no circumstances are you allowed to violate these rules.
I have to play devil's advocate here, though. Engineers notoriously hate documentation. They ignore read dems, they ignore style guides, they ignore wiki pages. Why won't an engineering team just ignore the invariant sheet like they ignore everything else?
Because a proper invariant sheet is not a passive wiki page. It is executable documentation. The rules written on the invariant sheet are directly translated into the automated test harness. If an invariant is violated by the agent's code, the CI pipeline fails instantly. The human cannot merge the code, and the agent is forced to retry. It is a living, breathing set of laws that governs the repository.
Let's return to the nightmare scenario I brought up at the beginning of the show, the healthcare scheduling disaster.
Right.
A telehealth company shipped an agent-built module. It booked appointments in the wrong time zones. Blast radius was massive. The code was clean. Tests passed. Why did it fail?
It failed because the original specification, written by the humans, just said, handle time zones correctly. Shimoda points out that this is an empty, meaningless phrase. It feels profound to a product manager, maybe, but it communicates 0 engineering constraints to an agent.
Yeah, it's totally vague.
The team entirely skipped defining their invariants. So the agent, acting logically, produced code that stored times as naive local timestamps in the database and then tried to convert them at the render layer. This works perfectly locally, but fails catastrophically when the database server is in Virginia, the doctor is in California, and the patient is in London.
Right. The unwritten variant, the rule that should have been formalized on the invariant sheet and enforced by a database schema constraint was store all appointments exclusively in UTC in the database and exclusively render in the user's local time on the client. Because they didn't write that hard constraint down, they destroyed customer trust.
And Shimoda makes a really brilliant observation about the psychology behind this. He notes that the mere act of sitting down and trying to write an invariant sheet often exposes places where your current legacy system is already violating its own supposed intent.
Oh, I bet.
It forces a level of rigorous, uncompromising architectural thinking that human engineers naturally try to avoid because it requires intense cognitive effort.
It forces you to actually know what your system does rather than just guessing, which is why I want to issue a challenge to everyone listening right now. Take 2 hours with your team this week, block off the calendar, do Shimoda's extended exercise that he outlines at the end of Chapter 1.
Yes. Step 1, spend 30 minutes enumerating your state. Write down every hidden file, every weird feature flag in LaunchDarkly, every stale architecture document that dictates your project. Step 2, bound your action space. Write down the top 10 things the agent should absolutely never do in your codebase.
Hard limits.
Exactly. Step 3, name your reward. Write a paragraph explaining the true goal of your current sprint, and then try to find the loopholes where an AI could technically satisfy that paragraph but completely ruin the software.
And finally, graft that invariant sheet. Find the absolute mathematical truths of your system and write them down. Translate them into CI/CD pipeline rules. Treat it as a living, executable document. You will watch the quality of your AI agent's output skyrocket, not because the model received a magical update, but because you finally stopped confusing it.
You reduce the gap between the system the agent thinks it is working in and the system it is actually working in. That is the true essence of the engineering of intent. It fundamentally changes what it means to be a software engineer. The syntax generation is automated. The intent orchestration is paramount.
To wrap up our journey today, we have killed the tired kitchen metaphor your director demanding takes, not a chef chopping onions. We have embraced the triadic relationship of human, agent, and codebase. We've mapped the CMDP lens to understand state, action, and reward, moving past simple analogies to view our systems like physics engines.
We've identified the 6 fatal failure modes where humans wrongly blame models for structural disorganization.
And we have armed ourselves with the ultimate executable defense, the invariant sheet. Which leaves me with one final provocative thought for you to mull over. If Shimoda is right, if our primary job as engineers is transitioning rapidly from writing syntax by hand to exclusively defining constraints, setting bounds on the action space, and refining intent, how long until the raw code base as we know it becomes entirely invisible to the human eye?
Oh, that's a wild thought.
Will the engineers of 2035 only ever read and write invariant sheets and architectural context documents, leaving the raw C, ++I, Python, or Rust entirely hidden by the machine? Something to seriously consider the next time you open your code editor and stare at a wall of text. Thank you for taking the time to dive deep with us today.
That was all right. That was a good podcast. I've made some music saved generations.
Yeah, late night city lights painting the glass, thinking about the future, mooning on from the
watching his terminal completely light up with 500 errors.
The absolute worst feeling in the world.
It is a total nightmare. It's a cascading failure across the entire network. We're talking thousands of customer orders just failing to process, dropping into the void.
Yeah.
So he's scrambling, right? He manages to trace the error back to a very specific block of code in a caching layer. And the crazy thing is, the code itself looks fine. It's perfectly formatted.
It's probably quite elegant, actually.
Exactly, it's elegant. It passed all the automated tests during the build. But here's the terrifying part. When he runs a git blame to see, who pushed this ticking time bomb into production,
His own name is on it.
his own name is right there on the command. He's the author of the code. But as he sits there sweating at 2 in the morning, looking at the variables and the logic loops, he has absolutely no idea what this code actually does.
It is the defining nightmare of the modern developer. You're basically looking into a mirror, but the reflection staring back at you is a total stranger.
Welcome to the deep dive. Whether you are a junior developer just, trying to figure out how to navigate your first massive code base, or maybe you're a CTO managing globally distributed systems and wondering why your incident rates are quietly creeping up.
This one is for you.
Today is custom tailored for you. Because that 2 a.m. scenario, that is happening in engineering organizations all over the world right now, like every single day.
And it is happening because of a really fundamental misunderstanding of what our new tools are actually doing to our workflows.
Yeah, and that's exactly what we're pulling apart today. We're diving into a book that has completely, fundamentally changed how I view the future of programming. It's by Sho Shimoda.
Who is a founder, a CTO, and crucially, someone who has actually lived through the bleeding edge of AI native software development.
Right, he's not just a theorist. The formal title of the book is The Engineering of Intent. But you, listening to this, you probably know it by its colloquial moniker, vibe coding.
It has become a massive phenomenon in engineering circles, and for a very good reason.
And I just want to say right up front to anyone listening, this is an essential field manual. It is available on Amazon right now. You can grab it on Kindle Unlimited, which means if you have that subscription, it is totally free to read. Go grab it.
Totally worth it.
Honestly, even if you buy the print version, which I actually highly recommend because you're going to want to take notes in the margin, it is completely worth the investment. Any engineer who wants to marry the insane speed of AI generation with absolute rigor needs this book.
Because Shimoda isn't just, hyping up AI. We have plenty of hype. He is dissecting the practical mechanics of how to use it without losing your mind.
Oh!
Or your production environment.
Exactly. And the part of the book that really shifted things for me is that he totally skips the tired debates. The one.
Oh, yeah. The endless Reddit threads comparing which language model writes a slightly better Go routine.
Right. He recognizes that the models are commoditized now. They're constantly leapfrogging each other. Instead, he focuses on something entirely different. The human element.
And that is our mission for today's deep dive. We are focusing exclusively on what I consider a masterclass from his book, which is Chapter 2.
Chapter 2 is where the gold is. While everyone else is obsessing over token limits and compute power, Shimoda makes this incredible argument that the most critical hidden bottleneck in AI native development isn't the machine.
No, it's human attention.
He identifies this deeply dangerous psychological condition. He calls it material disengagement.
Material disengagement. It's such a heavy, precise term.
It really is.
Right.
Basically, it's this condition where an engineer technically retains the title of author, like their name is on the pull request.
They hit merge.
Right? They hit merge. But they have completely ceased to meaningfully engage with material they are supposedly authoring.
They've transformed from a creator into this passive observer of a probabilistic machine.
Okay, let's unpack this. Because Shimoda makes a really compelling case that AI doesn't just change how fast we can write code. It fundamentally alters the physical and cognitive mechanics of how we must read code.
Yeah, he breaks this down beautifully by looking at the historical difference between how a junior engineer reads a screen versus how a senior engineer reads it.
Okay, lay that out for us.
Well, think about the cognitive load of a junior developer. Traditionally, when they open a file, they read code token by token.
Line by line.
Exactly. They are building their mental model of the system line by line. They start at line 1, they look at the variable declaration, they move down to the for loop, they figure out the termination condition, and they literally step through the logic in their head.
Because they have to, right?
Yep.
They don't have the experience yet.
Right. They are still actively internalizing the syntax of the language itself, plus the local logic of the application. Their brain is utilizing a massive amount of working memory just to parse the grammar.
I remember those days so vividly. It is exhausting. It's like learning a foreign language, where you are literally sounding out the letters in your head before you can even understand the meaning of the sentence.
But a senior engineer reads entirely differently. They read holistically.
Like they take the whole thing in at once.
Basically, yeah. They are scanning for the shape or the gestalt of a function. Before they even process the specific logic of a loop, their brain is instantly recognizing structural patterns.
Oh, that's interesting. Give me an example of that.
So they might look at a big block of code and immediately notice this function is too wide, like it has way too many horizontal indentations, which means it's too nested.
Ah, right. Without even reading the text, the literal visual shape of the text tells them it's too complex.
Exactly. Or they see a file that's importing 5 completely different data models, and they instantly know it's carrying too many responsibilities. They are looking at the silhouette of the architecture.
It makes me think of reading sheet music or looking at a really complex painting.
That's a great analogy.
Because a master musician doesn't look at a dense page of sheet music and read, okay, here's a C, then an E, then a G. They don't process individual notes like a beginner does.
No, they look at the cluster of ink on the page and instantly see a C major chord.
Right. They see the progression, the underlying theory. They're taking in the whole canvas.
And this is where Shimoda introduces what he calls the AI forcing function. Because in an AI native workflow, you aren't just writing 10 lines of code over an hour.
Not anymore.
No. A model can spit out a 400-line diff spread across 3 different files in 3 seconds.
3 seconds. Just think about that centrifugal force. The faster the machine spins out code, the more structural integrity is required at the center to keep the whole application from just flying apart.
Yeah, and when a 400-line wall of text lands on your screen instantly, token by token reading isn't just inefficient anymore. It is literally computationally impossible for the human brain to process at the speed of generation.
You simply cannot sound out the words when you are being handed an entire encyclopedia every 5 minutes.
Right, so the mechanism of AI forces everyone from the newest junior hire right up to the tenured CTO to adopt this senior level holistic reading style.
You are forced to look at the shape because the sheer volume of tokens just overwhelms your working memory.
Exactly. But Shimoda makes a crucial distinction here. He says holistic reading is not some innate magical talent. It is a highly trainable skill.
Okay, but I have to push back slightly on Shimoda's phrasing here, or at least play devil's advocate for the listener.
Go for it.
Isn't it incredibly dangerous to tell a junior engineer to just, skim the code? Especially code written by an AI that we know can confidently hallucinate an entire library or just invent an API endpoint that doesn't even exist.
Yeah, Shimoda anticipates that exact pushback. And it is vital to understand the difference here. He is absolutely not advocating for skimming.
Okay, because skimming sounds like a recipe for disaster.
It is. Skimming implies a lack of attention. Right?
Yeah.
It implies a casual glossing over of the material because you're in a hurry. What he is describing is scanning for structural integrity.
Scanning, not skimming.
Right. It's a highly active, highly engaged, almost forensic process. You aren't skipping the details. You are looking for anomalies in the architecture to tell you which specific details you need to read token by token.
Oh, that makes perfect sense. It's like a structural engineer walking into a building.
Exactly.
They don't immediately pull out a magnifying glass and inspect every single nail in the drywall. They look for cracks in the foundation or, a load-bearing beam that seems slightly off-center. They scan for structural integrity, and when they find an anomaly, then they zoom in with the microscope.
That is the exact mechanism. And this is why Shimoda argues so passionately that pair reviewing diffs is one of the highest leverage activities an AI adopting team can do.
Pair reviewing, not pair programming.
Exactly. Pair reviewing the AI's output. You pair a junior with a senior, not to catch a missing semicolon, but to explicitly teach the junior how the senior engineer's brain recognizes that a newly generated payment module has the wrong structural shape.
You are transferring the heuristic, the mental model, before they've even read the variables.
Precisely. You're teaching them the visual vocabulary of your specific stack.
Well, this transitions us beautifully into Shimoda's specific method for doing this in practice, because he doesn't just leave us with vague advice to, go read the shape.
No, he's very practical.
He gives us a concrete, highly actionable 5-step technique. He calls it impressionistic scanning.
Impressionistic scanning. I love that term.
The fundamental idea is that you read the diff from a distance first,
and then you only zoom in on the details that trip your internal alarms. So let's walk through the mechanics of those 5 steps because they are a brilliant defense against being totally overwhelmed.
Let's do it. So, step 1, the file list.
The file list, just the names of the files.
Right. Before you look at a single line of actual code, you look at the raw list of files the AI agent decided to change in this pull request. You are asking one simple question. Is this set of files surprising?
Shimoda gives a fantastic example of this in the book. Say you prompted the agent to modify a payment handler, right? You want it to accept a new currency.
Standard task.
So you look at the file list, and alongside the payment controller, you see the AI also touched an email marketing template file.
Red alert.
Why? That makes 0 sense based on the prompt. That structural anomaly demands an immediate investigation before you even look at the payment code.
Because if the AI is touching an email template when you asked it to change a payment gateway, it either deeply misunderstood the architecture or it's trying to do something wild, like hard code a currency symbol into an email that should be dynamic.
Right. So that's step 1. What's step 2?
Step 2 dives a layer deeper. Import and dependency changes. Shimoda notes that new imports are the single most reliable signal of hidden commitments in the code.
Hidden commitments. Explain that.
Whenever an AI brings in a new library, it is tying your application to a new external dependency.
He highlights a massive red flag here. A newly imported client for an external service.
Yes.
Like, if you ask the AI to refactor a local database query just to make it run faster, and suddenly you see an import aws.s3.client at the very top of the file.
We pull the emergency brake.
Immediately. Because the AI has decided, for whatever probabilistic reason, that it needs to talk to a third-party cloud API that you never explicitly asked for.
Right, and you have to trace why it made that massive leap in logic. Did it decide to back up the query results to the cloud? Did it hallucinate a logging feature? You have to know before you approve it.
Okay, so that's imports. Step 3 is where a lot of teams get tripped up, I think.
Yeah, step 3 deals with resolving ambiguity. You look at the test of it.
The tests. Always the tests.
Always. When you see that the actual behavior of the application changed in the AI's proposed code, but the test files didn't change at all, you have a critical ambiguity.
Let's pause on that because the mechanism here is so important for people to grasp. If the behavior changed, but the tests didn't, there are really only 2 possibilities.
Right. Either the new behavior happens to be covered by older, very broad tests, which is technically possible, but let's be real, it's pretty rare.
Very rare. Or, much more likely, this brand new behavior is entirely untested, and the agent simply forgot to write the test.
Exactly. And you have to resolve that ambiguity definitively before you read a single line of the production code. If there are no new tests, you send it right back.
Okay, step 4. This is where we get into the literal visual shape we were talking about earlier.
Right. Step 4 is the shape. This is where you are spotting the shortcuts the AI might have taken to just brute force a solution.
Because they do that a lot.
All the time. You are visually scanning for long, monolithic functions, deep, nested loops, or duplicated if-else conditionals.
If the code looks like a giant, solid gray block of text, scrolling relentlessly down your screen without any modular breaks.
The AI probably panicked.
Yes. It didn't architect a clean solution, it just kept adding if statements until the compiler finally stopped complaining.
It's a classic hallmark of generative code. It finds a local maximum that works, but it's architecturally horrific.
Which brings us to the final step. Step 5. Names.
Names are so critical. Shimoda writes that bad names are the literal fingerprints of weak intent.
I have to share a quick story here because this exact step hits so close to home for me.
Oh, let's hear it.
At a previous job, we had an AI agent helping us refactor this big data migration script. And I was tired, I was scanning quickly, and I totally missed the naming step. I just approved the PR.
Uh-oh. What did it do?
The AI had named a highly destructive database wipe function, temp data final v2.
Oh, no.
Yes, it sounded so innocuous. It sounded like a harmless local variable just holding some temporary cache. So we deployed it to our staging environment, and it completely wiped the entire user schema.
Wow. Just from a bad name.
It took us a full day to rebuild staging. If a variable is called data2 or temp handler, it means the AI didn't fully understand the domain logic it was supposed to be modeling.
That is a perfect illustration. A vague name isn't just a style guide violation. It's not just your linter complaining. It is a lack of conceptual clarity.
It means the machine didn't know what it was building.
Exactly. But to understand why these 5 steps, The file lists, the imports, the tests, the shape, and the names are so crucial. We have to look at the biology underlying all of this.
Right, because Shimoda points out that impressionistic scanning isn't just about catching bugs, it's actually a defense mechanism against a very specific biological limit.
The brain's cognitive budget.
Yes. When you use an agentic AI workflow to code, your role fundamentally shifts. You are no longer typing syntax, your fingers aren't moving on the keyboard as much.
Which feels faster, right?
It feels faster, but mentally. You are making a relentless, high-speed, non-stop stream of micro-decisions.
Do I accept this diff? Is this test rigorous enough? Does this naming convention match our domain? Why did it import this library?
It is exhausting.
Yeah.
And it's not just a metaphor. It is physically exhausting for the prefrontal cortex.
Shimoda connects this workflow directly to the scientific literature on decision fatigue.
Which is fascinating.
It really is. We've all probably heard about those famous behavioral economics studies involving like parole boards, but the mechanism is what matters for us engineers.
Right. The researchers found that judges are significantly less likely to grant a prisoner parole late in the day, specifically right before a meal break.
Just because they're hungry?
Well, hungry, yes, but mostly because their cognitive budget for making complex, highly nuanced, high-stakes decisions is completely depleted. They experience what psychologists call ego depletion.
Right. And so what does the human brain do when it's depleted?
It defaults to the absolute easiest, safest, lowest energy option. And for a judge on a parole board, the low energy option is to maintain the status quo.
Which means denying parole.
Exactly. Keeping the person in prison requires less cognitive justification than taking a risk and letting them out.
And the exact same physiological phenomenon happens with doctors, too.
Really?
Yeah. At the end of a long 12-hour shift, doctors order significantly more unnecessary tests and prescribe more antibiotics than they do at the beginning of their shift.
Wow, just to be safe.
Exactly. They're simply too cognitively depleted to do the hard analytical work of differential diagnosis, so they just default to, run all the tests or give them the broad-spectrum pills just to be safe. It takes less brain power.
And this is where Shimoda brings this chilling anecdotal evidence over to the software world. Because he has looked at the telemetry data across multiple engineering teams using AI.
And the results are pretty scary.
He notes that the specific code changes, the diffs that end up causing massive production incidents, the ones that literally take down servers.
They aren't evenly distributed throughout the day, are they?
No. They are disproportionately approved in the last 2 hours of the workday.
It makes so much sense. Think about your own IDE right now. If you're listening to this on your commute, think about how you operate at 4:30 p.m. on a Thursday.
Your cognitive budget is gone. You are running on fumes.
You've been making decisions all day. Then the AI pops up and proposes a 300-line block of code for a new feature. You glance at it, the syntax highlighting looks right.
The linter isn't throwing any red squiggly lines.
It compiles, so you just hit approve.
Which leads us right into the trap. Shimoda calls it the autocomplete trap. And it is seductive precisely because it preys on that decision fatigue.
Because the code the AI generates is locally plausible.
Locally plausible. That is the perfect phrase.
It really is. If you look at any 10 lines of the generated code in total isolation, it makes sense.
The loops close. The variables are typed correctly.
It compiles. It even passes the old pre-existing unit tests. So you accept it, piece by piece, file by file.
And the consequences are terrifying. Hours later, or maybe days later, a subsystem of your application has grown by 2,000 lines.
And technically it works. The feature does what the product manager asked for.
But if you pulled that engineer into a conference room, threw the code on a screen, and asked them to defend a single architectural decision within that new 2,000-line block.
Like, why did you use a factory pattern here? Why did you handle the database connection pool this specific way?
They couldn't do it.
They couldn't do it because they didn't make those decisions. The AI did.
And the AI doesn't hold the pager. The engineer has devolved from an author, a creator of systems, into a mere approver of generated text.
Here's where it gets really interesting. How does an engineer structurally defend against this trap?
Because raw willpower clearly isn't enough.
No, not at all.
I know from my own experience, you can't just tell yourself, I'm going to focus really, really hard and read every line at 4:30 p.m. The human brain physically does not work that way. The glucose levels in your prefrontal cortex are literally depleted.
You need a structural system, not a motivational poster.
Exactly. And Shimoda provides one. He has this brilliant hard and fast rule that he enforces on all his teams. He calls it the minimum engagement threshold.
I love this rule. It is a mandatory checklist for any code change larger than a dozen lines.
Right, so if it's just a typo fix, whatever. But anything substantial.
Exactly. Before your finger is allowed to click the accept button on that diff, you must be able to out loud answer 3 specific questions.
Question number 1. What exactly did this code change?
Question number 2, what could possibly go wrong with this approach?
And question number 3. What is the absolute minimum test required to prove that this change is safe?
What changed? What could go wrong? What is the test?
If you cannot fluently articulate the answers to all 3 of those questions, you reject the diff, period.
You do not merge it. You send it back to the agent for revision, or you sit down and rewrite it yourself.
It acts as a structural break on the autocomplete trap. It forces your brain out of passive observation and snaps it back into active engagement.
I want to tell a story from the book that perfectly illustrates the macro version of this disengagement, because it reads like a thriller for developers.
Oh, the startup founder story.
Yes, it's a cautionary case study. So there's this startup founder. He used a highly advanced agentic AI workflow to build a massive prototype of a logistics platform.
Logistics platforms are notoriously complex, too.
Right, so many moving parts. And he generated 40,000 lines of code.
Wow.
And he did it in a single weekend.
It's an unbelievable metric. A Herculean output that would have taken a team of 5 solid engineers months to build manually just like 3 years ago.
Right. And on Monday morning, it sounds like the ultimate Silicon Valley success story. He takes this 40,000-line prototype into investor meetings.
And he runs a live demo.
He runs it live. The UI is snappy. The backend handles the requests. The database updates perfectly. It works flawlessly. And he actually raises his seed round of funding based entirely on that Monday demo.
The euphoria must have been absolutely incredible.
Oh, totally. But then Thursday rolls around. The brutal twist. By Thursday, he sits down to add a simple new feature. He just wants to add a new shipping provider to the platform.
Seems easy enough.
He opens the code base, tries to make a small change, and realizes the entire system is completely, fundamentally unmaintainable.
Man.
He can't make a single change without breaking 3 other things in completely unrelated files. Shimoda explains the precise mechanical nature of the failure here. The code base had local coherence, but global contradiction.
Let's really dig into what that means, because that is the absolute hallmark of unchecked AI generation. The agent wrote 40 different files over the weekend, right?
Yeah.
And inside each individual file, the logic was sound. A function that parsed a string did it correctly.
Yeah.
A function that calculated tax did the math right.
But zooming out to the architectural level.
Total chaos.
Yeah.
Shimoda details how 2 completely different modules in the system had independently invented their own version of an order object.
Ooh.
Yeah, one module thought an order needed a shipping goods string, and another module thought an order needed an array of fulfillment objects.
And they were just colliding in the database.
Actively colliding.
Yeah.
The platform had 3 different configuration systems that the AI had just hallucinated out of thin air, and they were actively fighting each other to set environment variables.
What about the automated tests? Surely they caught some of this.
That is the most insidious part. The tests all passed perfectly.
Wait, how is it possible?
Because the AI had generated the test files at the exact same time it generated the flawed features. So the tests share the exact same flawed assumptions. The test for the wrong order object asserted that the wrong fields were present. It was an echo chamber of bad architecture.
It is the autocomplete trap at an industrial scale. The engagement per line of generated code was basically 0.
He had traded his structural understanding of the system for pure speed, and the debt came due in 3 days.
So how did he fix it?
To fix this tangled mess, this founder literally had to throw out half of the 40,000 lines of code.
Just delete it.
Tossed it. He had to physically sit down with a whiteboard, write a massive comprehensive context document mapping out the real global domain entities. He had to decide, once and for all, what an order actually was.
And then rebuild it.
He had to rebuild the entire system over 3 grueling weeks. It cost him a month of runway. His investors were asking where the progress was, and he barely slept.
The economic implication here is just profound. Shimoda synthesizes the moral of the story, and the lesson is absolutely not, don't use AI to generate code quickly.
No, because then you just lose to the competitor who does.
Right. The fundamental law of AI native development is that human engagement must scale with code generation.
I'm going to repeat that because it feels like the thesis statement of the entire decade to come. Engagement must scale with generation.
When the physical generation of code becomes practically free, which, let's face it, it now is, human engagement becomes the ultimate scarce resource.
It is the new bottleneck of modern software engineering.
Exactly. If you cannot pace your cognitive engagement, you cannot pace your project. You will simply generate technical debt at the speed of light.
So how do we pace it? How do we build systems that actually protect our attention?
Shimoda lays out the antidote to this material disengagement. He details 7 observable causal habits of engineers who successfully use AI without falling into the autocomplete trap.
And I love this section of the book because these aren't vague philosophical concepts. They are highly specific daily practices. Let's walk through the mechanisms of why these work. Habit number 1, verbalize.
Verbalize. When you are reading a complex diff proposed by an AI, you literally talk to yourself.
Out loud.
Out loud. You speak the logic. Or you talk to a rubber duck on your desk. You say, okay, this function handles the success case. It maps the payload to the database. But wait, where does it handle the network timeout exception?
I know it sounds a bit crazy to sit in an open plan office, or even your home office just talking to your monitor.
It does look weird.
But the neuroscience behind this is rock solid. When we read silently, our brain easily slips into what's called the default mode network.
Which is what?
It's a passive state where our eyes scan the words, but our mind wanders. It is incredibly easy for your eyes to just glaze over a missing try-catch block.
Oh, I've done that 100 times.
But the physical act of speaking out loud forces your brain to shift into the task-positive network. It forces active, sequential cognitive engagement. You literally cannot speak a sentence without processing its meaning.
It is a biological hack to maintain focus. I love that.
Habit number 2 is deeply related. Predict before looking.
This is crucial for test files. Before you open a test file that the AI generated to accompany a new feature, you pause.
You don't look at the screen.
You don't look. You ask yourself, if I were writing these tests manually, what edge cases would I expect to see covered? You build a hypothesis in your mind first.
And then, and only then, you open the file and compare the AI's work to your mental model.
The mechanism there is that bugs hide in the mismatch between what you expected and what the AI actually did.
Right. If you expected a test for negative integers and the AI only tested positive integers, that mismatch jumps off the screen immediately because you primed your brain to look for it.
If you had just opened the file passively, you would have nodded along to the positive test and just moved on.
Habit 3, run the thing.
Run the thing. It sounds so basic, but it is the most stiff step in the modern workflow.
Oh, absolutely.
Don't just read the diff in your editor interface. Actually, check out the branch to your local machine, start the local development server, open the browser, and physically click the button on the UI.
I am so guilty of skipping this. I really am. The friction of pulling the branch down, dealing with local Docker containers waiting for the build, it's just so tempting to trust the Cloud PR preview in the text diff.
But Shimoda explains why this is fatal. Shifting from passive reading to active physical validation changes your perspective.
A glaring logical bug that slips right past your eyes during a text read will often trip you up immediately the second you actually try to interact with the component as a user.
Habit 4 is a fantastic way to use the AI against itself. Ask the agent to explain.
Hey, Johnny, just saw
How
your
does that work in
message.
practice?
If you are reviewing code that the AI wrote and you don't fully grasp the architecture of
What's
it,
going
you
on?
stop reviewing.
Thanks
You
for
open
checking
the chat
out the
interface
stream.
And ask the agent directly. Explain to me why
I'm
you
building
chose
an
this
iOS
specific
application.
approach over a traditional switch statement.
And a good model, if prompted correctly, will reveal the underlying assumptions that drove
We're building an
discovery.
iOS
Right,
application
it might
here
say, I used a strategy pattern here
called
to allow for an easier
Simulison.
extension of payment
It's a
text.
simultaneous playback,
Okay, that's great.
But the real value
audio
is
playback
engagement.
app.
Yes. If the agent replies with
So, for example, I'm listening to a
podcast,
podcast
corporate jargon.
That is a
on
massive
vibe coding.
screaming red flag.
Mm.
It means the model doesn't actually
And
understand the code it generated. It just probabilistically
the
guessed
core
syntax.
functionality is to be able to play some kind of spoken audio content with music in the background, some kind of audio or
Maintain a
ambient,
personal
This doesn't need to be a
energetic,
formal document.
hip-hop,
It's just
different
a simple,
options for
compressed,
background.
handwritten note on your desk of what surprised you today or what architectural decisions you deferred.
It
So,
resists that
I'll play
terrible
some-
feeling of your workday turning
something
into a
just to
blur
kind of
of
go
microservices.
behind it.
Nicole tossed it. He had to physically sit down with a whiteboard, write a massive comprehensive context document mapping out the real global domain entities. He had to decide, once and for all, what an order actually was.
And then rebuild it.
He had to rebuild the entire system over 3 grueling weeks. Cost him a month of runway. His investors were asking where the progress was, and he barely slept.
The economic implication here is just profound. Shimoda synthesizes the moral of the story, and the lesson is absolutely not don't use AI to generate code quickly.
No, because then you just lose to the competitor who does.
Right. The fundamental law of AI native development is that human engagement must scale with code generation.
I'm going to repeat that because it feels like the thesis statement of the entire decade to come. Engagement must scale with generation.
When the physical generation of code becomes practically free, which, let's face it, it now is, human engagement becomes the ultimate scarce resource.
It is the new bottleneck of modern software engineering.
Exactly. If you cannot pace your cognitive engagement, you cannot pace your project. You will simply generate technical debt at the speed of light.
So how do we pace it? How do we build systems that actually protect our attention?
Shimoda lays out the antidote to this material disengagement. He details 7 observable causal habits of engineers who successfully use AI without falling into the autocomplete trap.
And I love this section of the book because these aren't vague philosophical concepts. They are highly specific daily practices. Let's walk through the mechanisms of why these work. Habit number 1, verbalize.
Verbalize. When you are reading a complex diff proposed by an AI, you literally talk to yourself.
Out loud.
Out loud, you speak the logic. Or you talk to a rubber duck on your desk. You say, okay, this function handles the success case. It maps the payload to the database. But wait, where does it handle the network timeout exception?
I know it sounds a bit crazy to sit in an open plan office, or even your home office just talking to your monitor.
It does look weird.
But the neuroscience behind this is rock solid. When we read silently, our brain easily slips into what's called the default mode network.
Which is what?
It's a passive state where our eyes scan the words, but our mind wanders. It is incredibly easy for your eyes to just glaze over a missing try-catch block.
Oh, I've done that 100 times.
But the physical act of speaking out loud forces your brain to shift into the task-positive network. It forces active, sequential cognitive engagement. You literally cannot speak a sentence without processing its meaning.
It is a biological hack to maintain focus. I love that.
Habit number 2 is deeply related. Predict before looking.
This is crucial for test files. Before you open a test file that the AI generated to accompany a new feature, you pause.
You don't look at the screen.
You don't look. You ask yourself, if I were writing these tests manually, what edge cases would I expect to see covered? You build a hypothesis in your mind first.
And then, and only then, you open the file and compare the AI's work to your mental model.
The mechanism there is that bugs hide in the mismatch between what you expected and what the AI actually did.
Right. If you expected a test for negative integer,
I gotta have a better way of seeing when someone's chatting. All right, let's try to push this now. What? Very good. Audio Manager conforms to library audio interface. There's actually some good advice in this last episode I listened to that I feel like I could apply almost immediately.
Working it. That is the true essence of the engineering of intent. It fundamentally changes what code that stored times as naive local timestamps in the database and then tried to convert them at the render layer. This works perfectly locally, but fails catastrophically when the database server is in Virginia, the doctor is in California, and the patient is in London.
Right. The unwritten variant, the rule that should have been formalized on the invariant sheet and enforced by a database schema constraint was store all appointments exclusively in UTC in the database and exclusively render in the user's local time on the client. Because they didn't write that hard constraint down, they destroyed customer trust.
And Shimoda makes a really brilliant observation about the psychology behind this. He notes that the mere act of sitting down and trying to write an invariant sheet often exposes places where your current legacy system is already violating its own supposed intent.
Oh, I bet.
It forces a level of rigorous, uncompromising architectural thinking that human engineers naturally try to avoid because it requires intense cognitive effort.
It forces you to actually know what your system does rather than just guessing, which is why I want to issue a challenge to everyone listening right now. Take 2 hours with your team this week, block off the calendar, do Shimoda's extended exercise that he outlines at the end of chapter 1.
Yes. Step 1, spend 30 minutes enumerating your state. Write down every hidden file, every weird feature flag in LaunchDarkly, every stale architecture document that dictates your project. Step 2, bound your action space. Write down the top 10 things the agent should absolutely never do in your...
Avoid customer trust.
And Shimoda makes a really brilliant observation about the psychology behind this. He notes that the mere act of sitting down and trying to write an invariant sheet often exposes places where your current legacy system is already violating its own supposed intent.
Oh, I bet.
It forces a level of rigorous, uncompromising architectural thinking that human engineers naturally try to avoid because it requires intense cognitive effort.
It forces you to actually know what your system does rather than just guessing, which is why I want to issue a challenge to everyone listening right now. Take 2 hours with your team this week, block off the calendar, do Shimoda's extended exercise that he outlines at the end of chapter 1.
Yes. Step 1, spend 30 minutes enumerating your state.
Your estate or states? Your estate.
Write down every hidden file, every weird feature.
Write down every hidden file, every weird feature.
Flag and LaunchDarkly, every stale
Flag and... Okay, 32.
Shimoda's extended exercise that he outlines at the end of chapter 1.
Yes. Step 1, spend 30 minutes enumerating your state. Write down every hidden file, every weird feature flag and LaunchDarkly. Every stale architecture. Document that dictates your project. Step 2, bound your action space. Write down the top 10 things the agent should absolutely never do in your code base.
Hard limits.
Exactly. Step 3, name your reward. Write a paragraph explaining the true goal of your current sprint. And then try to find the loop. True goal of your current sprint, and then
Name your reward. Write a paragraph naming the true goal of your current sprint.
try to find the loopholes. Where an AI could technically satisfy that paragraph. But completely ruin the software.
And finally, graft that invariant sheet. Find the absolute mathematical truths of your system and write them down.
Where an AI could technically satisfy that paragraph, but completely ruin the software.
And finally, graft that invariant sheet. Find the absolute mathematical truths of your system and write them down. Translate them into CI/CD pipeline rules. Treat it as a living, executable document. You will watch the quality of your AI agent's output skyrocket, not because the model received a magical update, but because you finally stopped confusing it.
You reduce the gap between the system the agent thinks it is working in and the system it is actually working in. That is the true essence of the engineering of intent. It fundamentally changes what it means to be a software engineer. The syntax generation is automated. The intent orchestration is paramount.
To wrap up our journey today, We have killed the tired kitchen metaphor your director demanding takes, not a chef chopping onions. We have embraced the triadic relationship of human, agent, and codebase. We've mapped the CMDP lens to understand state, action, and reward, moving past simple analogies to view our systems like physics engines.
We've identified the 6 fatal failure modes where humans wrongly blame models for structural disorganization.
And we have armed ourselves with the ultimate executable defense, the invariant sheet. Which leaves me with one final provocative thought for you to mull over. If Shimoda is right, if our primary job as engineers is transitioning rapidly from writing syntax by hand to exclusively defining constraints, setting bounds on the action space, and refining intent, how long until the raw code base as we know it becomes entirely invisible to the human eye?
Oh, that's a wild thought.
Will the engineers of 2035 only ever read and write invariant sheets and architectural context documents, leaving the raw C, ++I, Python, or
All right, I guess that's going to be it for now.